So I decided to cover this paper today. Learning to execute, actually the full title is addition. Learning to add, multiply, and execute algorithmic instructions exactly with neural networks. And this is how we are connecting to the previous lecture. It turns out that somehow you can massage neural networks to do all of these things. Maybe it's not super surprising given what Dale was also talking about, right? So I suppose he was talking about how transformers can be also massaged into universal in some computational sense. The goal of this paper is very similar.
What Dale was talking about didn't require transformers, right? It was just any neural, like even a perceptron.
It was not.
Yeah.
Okay.
Because the perceptron just takes some symbol, produces a new symbol.
But the proof was on a transformer. Like the proof
Yeah,
was by existence.
but it did not require a transformer because all you needed was something that maps like three symbols to two symbols or something. Anyway.
Yeah. This paper is somewhat similar to that. So there is neural nets in the title of the paper, and the whole a big part of the paper is devoted to massaging neural nets to do the things we want them to do. But the way this works is that you somehow devise something like bit operations or bit string operations that manipulate bit strings in a certain way, and then you massage neural networks to do those bit operations, and the bit operations are going to be what are used to represent this arbitrary sequence of computations that you wanted to do. So it's done in these two steps. So first you are using, like they call this the template matching framework. And so first I will talk about that. So the template matching framework is used to simulation of specific algorithms. And like addition, multiplication, but then it turns out that you can use it to simulate an algorithm, which is this subtract and branch if negative, this elementary building block if negative, which has some universality properties, therefore you'll be able to basically simulate any algorithm. And so the idea here is that you're going to represent computation by mapping some binary vectors to some binary vectors. You can think about that represents the current state of computation, and then you write the input somewhere, and then you have this map that's manipulating this binary vector, and you keep applying it until some termination condition holds. Let's say 0's bit equals 1, then you stop, and you have a readout procedure that reads out certain bits. And that's how you represent the computation. So there is this map F, whose iteration is going to define the computation. And somehow, in this template matching framework, Well, I would talk about like why, like, so you choose this function f in such a way that somehow we can create small training sets to train to neural networks to train the whole f to the neural network. So these will have many bits. Earlier we have seen that if you do things naively, you will fail. If you just try to learn maps, even when you had only one output on some examples, don't do that. So you choose something really specific here, like these maps are restricted. Somehow we'll be able to do this, that we're going to learn the map like sufficiently well so that once a neural network is representing this map, so that will be a training procedure. And I guess this is maybe what Leo was not really mentioning when revealing that. But was he talking about how you can train this thing?
And also, Dale was saying that arbitrary randomly initialized neural networks will already have the right properties.
Right.
So you can train an encoder to transform you can find the symbols that have the behaviors you need given an arbitrary
Yeah.
neural network.
Yeah.
Which is the same thing basically.
Well, it's kind of the reverse of what you want, because so that somehow says that if you take a big enough randomly initialized neural network, then that represents a rich enough set of transformations of the input so that you can represent any computation with the iteration of that.
Well,
But
so-
that doesn't tell us how exactly we could do. So if my purpose is that I have numbers that I want to add, so let's say binary addition, I want to implement binary addition. Then using this procedure, it's not trivial how I do, like I randomly initialize my neural network, and then I have to run a search procedure to find out how the neural network is implementing my binary addition.
So here is the input going to be like the vector, like the thing on the vector, like the number you are adding?
So here, I have the purpose of implementing a specific calculation, like adding binary numbers.
But with a fixed length or?
Fixed length.
So it's like a finite state machine?
It's a fixed length computation that,
Okay.
that we want to represent. The universality properties, I will not go into what the universality properties are, but it's similar to the circuit complexity that if you scale the number of bits, then this can represent anything and like, okay.
Yeah, because what Dale was talking about was that you have some external memory and you just need to train this thing to be the state machine of a universal Turing machine.
Yeah.
And then you can implement any algorithm, but that algorithm won't be implemented in the neural network. It will be put on your memory.
On your
and
tape, yeah.
And so the neural network doesn't need to learn anything. It just needs to represent the transition
right.
function of a universal Turing machine.
Yeah. So there you, this is very similar to that in a way, but the neural network itself is going to do more of the heavy lifting of doing the computation. So if you have an algorithm in mind, then you rewrite the algorithm on some specific language, and then once you rewrote the algorithm on the specific language for a certain bit length, you can then design the training data, and then you train some neural network. And after the training of the neural network, or neural networks in this case is done, you can use the neural networks to do exactly the computations on that many number of bits that you decided to use.
And what if the computation needed like a lot more memory than like the size of the input? Then it doesn't work.
I mean, no. You decide about how much memory it needs. So that's also a parameter. So it's not limited by that. So it's basically you decide about like how many bits represent the inputs, and then how many bits represent like are allocated to the memory, or how much memory you need, and then this thing can do it. All right. Okay, so at a high level, this is how it works, and I think that what's kind of unique in this approach is that the neural nets are going to do more of the computation than in some other approaches. But it's also, I don't know, you will see, it's kind of weird. You still do a lot of the heavy lifting, so this doesn't really solve the problem that we had, which was that on natural language, you want to write out what you want, then this would do the same. So it's not easy to mix, like it doesn't have this property that it would be easy to use this approach together with the ability to pick up knowing about the language, natural language. It's just doing symbolic computation. What is different to, like, sometimes people, like Vlad was talking about these representation results. Let's say that neural networks are rich enough to represent, like classes of functions, they can represent computations. So here the weights, like there, we prove that there exist weights that you can set to the neural networks such that they represent the computation you wanted. Here, you use gradient descent with a neural network with a certain architecture to get those weights. So that's a little bit closer to our goal. So this sits somewhere in between of where we want to be, and these very early initial results that are just talking about the representational power of neural networks. It's going in the right direction, but it's very far from being there. Yes.
What's missing? If you can learn the weights, what else do you want?
I don't want the input to be in this very weird format, like that's one thing. And the other thing is that I have to do the heavy lifting of rewriting my algorithm in their special language.
So this is effectively, so you have a finite state machine in mind, and you want the algorithm to reproduce that.
Yeah.
The set of things that a finite state machine can do is effectively a regular expression. So effectively, we are writing a regular expression compiler to the weights of a neural network, right? It seems like that's computation in a very limited sense, right?
I'm not that much worried about the computation being that limited. I'm more concerned about that none of these things generalize to be friendly to language, learning language.
Because I mean,
they are just like the input space suddenly became something very different than text. It has nothing to do with text.
But I mean, you could think of that as text, but the problem is you only have a finite amount of text. And it's basically like you're running a send command over and over again on some text. And then when something happens, it stops. And that's all you're doing. You're trying to figure out what regular expression to give to my string like replacement routine such that it reproduces the computation I want. But that's pattern matching, right? Pattern matching of finite length patterns repeatedly until you get a pattern you want, and then you're done. Without like growable memory. So
The growable memory is the biggest concern again.
yeah, anyway, maybe I'm being overly reductive. But that's the point of computer science, is to be reductive, right?
Yeah. Anyways, I said that it's good to see the details of something like this,
Yeah.
just to understand what it involves to do something like this. I wouldn't recommend doing this, by the way. I'm happy that someone else writes these papers. It's not, because it's a lot of work, actually. Like, it's a lot of busy work to do it. And at the end of the day, it's not very clear how useful it is or how insightful it is. The high level structure, it's kind of interesting to understand these aspects that okay, earlier we have seen that naive approach to training a neural network to solve some problem like this can fail. And then here we are looking at some subclass of functions for which we can somehow massage the neural networks to do this right thing. Like they're correct on every input that we care about. And there will be exponentially many inputs. And they're correct on all of them. I thought this kind of maybe interesting. Yeah.
To make some connection to the previous lecture, are they making some assumptions over H star in the notation of previous lecture or in the input space?
What was H star? Oh, H star. No, yeah. Like everything. H star, everything.
Oh.
Like we're constructing this set of maps. They're not arbitrary sets of maps. There are certain maps that are learning friendly.
And
That you just represent, partial information about the maps, and somehow the neural network is able to pick it up. Right? Like this extrapolation problem that you have an exponentially sized domain and you want a small teaching set for certain maps, this is not a problem. And so here they are able to demonstrate this for something that's rich enough so that you can push every computation into it in a certain way. It's kind of neat in a way.
And they don't get to that lower bound in distance.
Yeah. So it's not subject to a lower bound, right? Like it's gonna everything is going to be polynomial in everything that you care about. So that's good. All right. So let's get to it. Yeah. All right. So the computation is going to be represented with this iteration. So you will have an initial vector which you obtain by encoding the input, which maybe lives in some other space. And after that, you just iterate by some bit. So all of these xt vectors, they have k bits, they are binary, and h is a specific bit, address, and why that bit is 0, then you're doing your iteration. And once this finishes, then you are returning something. So this decode and encode functions, they're just reading and writing certain bits, not anything complicated. And maybe as an example, we should go through how to use this, let's say, for adding numbers. But before that, I want to introduce the general form for this map F that we will be allowed to use, which will be friendly to this training procedure. So that's kind of, I think, the key innovation of this work, that they introduce this specific forms. So the input is going to be partitioned into B blocks. So block 1, block B. Yeah, right here. Block B has SB bits, this has S1 bits, the ice block has SI bits. All right. That is the corresponding address space. B1 is the positions for block 1, BI is the position for block I, the indices for which block I is active, and BB is the same for block B. So this is in the what's K is the total number of bits that we're going to use. So these are intervals in first K natural numbers. And the functions that we're going to allow are going to take the following form. Fx is the union, or of I functions, that each of the functions acts only on SI bits. The ice function acts on SI bits. It returns K bits. So this notation means that we are taking those bits which are in BI. And these BIs are just these intervals. Okay, so TI is going to be those vectors, everything is X. In the SI bit strings, for which tau I, X, returns non-zero. This is the support of tau I. Oh, Ti is the coordinate of the support, is the number of elements in the support, the number of times this function tau I returns something non-zero. Okay? So this is the combinatorial structure that we're gonna have.
And non-zero means it's zero.
Not zero vector,
Zero vector.
because, I mean, like, these are, yeah. So, why zero? Well, when you're ordering zero to something else, you don't do anything. Those things don't need to be remembered. So the training procedure will need to encode, if I want to encode a function f, how much information do I need to present to the neural network or whoever wants to know my function f? It is sufficient to look at the vectors in the support of each of the component functions, because the zeros don't matter. For each of them, I should record what is the vector on which this function is non-zero. Okay, that's one thing. And I should also record what was the response. And then this information uniquely identifies the function f. Okay? So we are going to actually need this. So the support of tau I is going to be this xi1, xi2, ti, these vectors, okay, and I guess that's all. So once you have these vectors and you have the values that tau I takes on these vectors for each I, for each of the blocks, you have encoded all the information about your function f.
Sorry, sum of ti many vectors in 0,
Right.
1 to the k.
So altogether, the number of examples that we're gonna need is that for each of the blocks, we have ti training examples. So this is the total number of training examples that we're gonna need. We're going to have. Okay.
What's the encoding process? There's no encoding yet? Is it just the F applied on?
No, so far we are just talking about some functions for which training might actually work. And on one hand, we're gonna say that these functions are sufficient to represent arbitrary calculations, like they're powerful enough to represent the calculations that we are interested in. And on the other hand, we're going to say that, well, they can be taught to neural networks.
So basically the neural network function class should contain these functions.
Yeah,
And then you should be able to learn.
yeah, efficiently. Yeah. Which,
What the exact, yeah.
there will be some cheat there. But,
I don't know how the exact part is gonna come out, but.
well, the exact part is, yeah, like it's not obvious to see yet. All right, but first maybe let's talk about why. So they call this the template matching framework. Why this language? Well, they are thinking about that this is kind of a template. You kind of match it. So this computation of f, you can think about it. This is how it works. Like you have this partitioning of the inputs, and then you look at each of the parts, and then you have a template library for that part with desired responses for that part. And so you go through your template library. If you see a match there to these are the vectors in your template library for the ice block. If you see an exact match, you have the corresponding response. You write down that response, and that's how you fill block by block the output. This, okay, so the tau I also has the property that tau I on any x returns a vector that outside of bi is 0. Yeah, I didn't tell you that. Is it? No, that's not true. That's absolutely not true. Okay. Yeah. So this picture is not the right one. So the first block, based on the first block, you choose a vector. Then based on the second block, you also choose a vector. Maybe it's a 0 vector if there was no match in your library. And you do this for all the blocks up to the end. And you take the OR between this. And that's the result of your computation. Okay.
So if any of the functions returns a 1 in the first position, that means
That will be 1.
and
So
that
these
means
positions will be carefully chosen so that, like only useful interactions happen. So since we are choosing here everything, when we are encoding some computation, we will be very careful with this. Okay.
And how do we exactly choose blocks, sort of independent something?
So Okay, why do we have the block? The reason we are going to have the blocks is because they will be helpful to encode specific algorithms. And so let's see an example of adding 2-bit numbers. Okay? So when you add 2-bit numbers, then the block structure is going to be, so you will have one number that is P1, P2, and another number which is Q1 and Q2. So this is the least significant bit, and this is the most significant bit. All right? And we are going to need some carries. We're going to have some carry for the overflow that resides when you're adding the first bits. So that will be C1, and we're going to have C2 as well. Maybe I should write it the other way. And I guess like filling out in some order this. In this case, if we're adding 2-bit numbers, then we're gonna have altogether 6 bits allocated intuitively to these individual bits. And the input and output encoding is going to be that at the beginning, we put the input bits here, the carries are set to 0, and then in the output, we're going to want to have the output to be these bits, the P bits and the carry. This is the output. This is the code function is reading these bits. Okay, so that's where we want to put the output of calculation. So now we want to, with this allocation of the blocks and the design of the blocks, we want to figure out what exactly these individual tau I functions are going to be. Yes,
Can the blocks have some overlap with each other, or they are separate?
they are separate.
So there's like 4 blocks.
Let me see. Yeah, I think, okay, so the calculation is going to be, obviously we have to look at P1 and Q1 together. And then based on that, we calculate the carry. And then based on the carry, and Q2 and P2, so based on P1 and Q1, you calculate the new value for P1 and C1. And then I'm just thinking about whether C1 should be propagated separately to here, or you treat these guys together as a block. I don't remember that. Maybe treat them together, then this would be another block. And maybe the third block is just C2.
Does P1 store the least significant bit of the result?
Hmm?
Does P1 store the least significant bit of the result output?
Yes. So if we start to fill, okay, so the first block is definitely this. Okay. So now, if we have on this 0, 0 should not result in any writing, so we can ignore it. We already agreed that if the output kind of thing would be 0, then you just ignore it. When you have 0, 1 as an input here, then you want the vector to be, you're gonna zero out things that you have used. But in the output is put to P1, so that's where you are going to run it. And, okay, so then 1, 0 should be written to 1, 0, and otherwise the same. And then 1, 1, so that's where carry is going to happen.
Mm-hmm.
Then you are zeroing these out, and then the carry happens. Okay. Okay, so now let's think about whether we want to treat this as a separate block. No.
I think all the
We really
three
have to do it
yeah.
together with these guys. It's not possible. So the next block is going to be this. So that is the case when the carry is 0. The all 0, it doesn't matter. When you have 1, 0, then the vector that you're writing, so this corresponding component, so there is only one bit above it, and you keep the 1, Q2 is 0, and this remains 0. Then the 0, 1, 0, that should be mapped to 0, 1, 0, 0, and of course everything is 0 here. And the 1, 1, 0 should be mapped to 1, 0, 0, 0, and all the zeros not needed. Now, if you have 1, 0, 1, so the 1, 0, 1 is the same as this, right?
Actually, we can't have 1, 0, 1.
Huh?
The carry is always 0.
No, the carry, the previous calculations could result in a carry. You're iterating until you finish or something.
I think in the first, the top case, I think the first bit needs to be a 1, otherwise the machine will halt. If you're, in the top of the board, those two cases, so there you're setting the carry bit, but then you also want the computation to keep going.
Yeah, so I'm not dealing with the computation keep going. For simplicity, I just say that we run this for 2 steps, and then we stop, because I could easily encode the end of the computation by, if I know that there are m steps, then a bit is wandering down, and then that's boring. I just don't do it. Okay, but correct. But okay, so to address whether the carry is always 0, after the first iteration, it's not 0. If the input was 1, 1, and the LSBs, then the carry is 1, so it's not 0. So when you iterate once more, then you are doing the carry, you're processing the carry. So you can have the 1, 0, 1.
But maybe we are finished already, because I think C2, P2,
No.
P1 is the answer. Because
Well, definitely, C2 is never set yet.
it was just 1, 1, 0.
It was never set to 1.
Oh, yeah,
Well,
yeah.
okay, only once, but how about
Yeah, sure.
all
Yes.
these other cases?
Yeah.
So the 1, 0, 1 case is the same as this case, and obviously the 0, 1, 1, that's symmetrically also this case, right? And then there is a case when we have all 1s, and then in that case we have 1, 1, and then all 0s. Okay. So if you define the function this way, obviously this implements f, the underlying f is going to implement binary addition on 2 bits. So the next question is, okay, this is cute. How about something more complicated? They do two other examples, permutation and binary multiplication. Permutation is trivial, even easier than this, and multiplication is just complicated enough that I don't care, because it is still very specific. So how about generally, like how powerful is this framework?
Mhm.
And so for that, they bring up this one instruction code type of universal computation, which works as follows. So this subtract and branch works with a memory structure that we're gonna need, and an instruction pointer. So the instruction pointer can point to one of the instructions. Every instruction is going to take this SBN form. That's why it's called one instruction coding or something, because there is only one type of instruction. And the instruction itself is going to have three parameters, A, B, and C. And the way it works is that you set the value of the memory at B to be the difference between MB and MA. And if MB is negative, then the instruction pointer is set to MC. No, it's set to C directly. And as nothing happens. As the instruction pointer is set to I+1. So the way the machine works is that you write down instructions. So the instructions are going to take the form of A and B and C with valid values up to M of these. So an algorithm is coded like this. This receives the index 1, or instruction count 1, and this is instruction count M. At the beginning, if you have an algorithm described by these parameters, you set the instruction counter to 1, and then you start to execute. So you take the value of A1, B1, and C1, and then with that execute this little subroutine that says the new value for I, and then you look up the next instruction at position I. And this has some universality properties. So you should believe that this is general enough. Yeah. I know, lambda calculus will be cooler, but
No, I mean, this all just comes down to like tricks for implementing small Turing machines using small amounts of
yeah.
like everything from the 70s is new again.
No, it's well, you're loading the Turing machine into a neural network.
Oh, yeah, sure.
Yeah. It's like earlier it was easy to just write these little things and then prove their universality. no, we also demand that there is a neural network that kind of can be trained to implement this thing, and that's what you are adding on the top
So like
of
in
what
the,
existed before.
in the 70s when they showed that neural networks can implement any function, and Turing machines can be implemented using small functions. But
That's
they're
right.
putting those together, and now you're saying,
I mean, that was also done in the 80s. These things were put together in the 80s.
so this is this decade's version. Okay.
I think that here, the new part is that there is some claim that something can be trained. So neural network, it's not like that I'm setting the weights of the neural network in like, so that was what like, so there were constructive ways of setting the weights of the neural network so that they implement the functions you want. Okay, that was done already 80s, earlier, this representation theory. It's a slightly different claim to say that you can take gradient descent and also train this thing, and the training is not going to take so much time. It doesn't need that many examples. So there is maybe some contribution there. I think that there is some contribution there.
So here we are going to train a neural network to implement this small Turing machine, right?
We're gonna, yes, we're gonna have a neural network. So when you take this and you take like this is the program,
Right. And the
and
program
you
is
want the neural network to represent the program. So we're gonna create training examples that represent this whole thing, not just this, but the whole thing. And so this is kind of neat. And you don't need a lot of training examples. The reason I like this better because, okay, for addition, we kind of see how to do it. Then you see it for multiplication, permutation, it's like only for these things. Okay, there's some universality here, right? Like if you, once you have done this, you don't have to ask these questions about like, but okay, how about other bit manipulations? Can I train neural networks to do all of those things? Yes, you can. And the training is not going to be intractable in terms of like the bit lengths and how many instructions you have here and how many steps this program needs to take. Yes.
So I was wondering how this FBM connects to those blocks. Are you just saying that?
I will use blocks to represent programs like this. So here, so there we were talking about binary addition. I can represent it with blocks. But why binary addition? Why not this? Why not that? Where to stop? What to look at? If you look at this, this is universal. If you can represent this with, like you can make you can create training data and run SGD on it, and the result is going to be that the neural network implements this program for any of the settings of ABCs and the M and like everything, and everything is polynomial, then you're kind of done with this question. You can load using SGD any desired algorithm into a neural network, not just know that like you could set the weights with like some human weight, but even gradient descent with some, like it's one step further along the way of creating neural networks that do what you want to do. Still a bit artificial because we have to do the heavy lifting of creating the training data. So first, I have to write my program with SVM. Then, there will be the procedure that creates the training data to train my neural networks. Then I run SGD, then my neural network will implement the program.
So is like each AI, BI, CI like one block? And you have these M blocks or like,
Yeah.
okay.
I mean, like, no. The blocks, we're gonna have many more blocks. I need to represent memory,
Okay.
instruction pointers, branching. This code, actually, I need to represent what this does. It has many steps, so it's a lot of suffering. This is what they do in 10 pages, and like it's hardly explained. And I will not try to explain it. But you can somehow see that if we could do this with addition, somehow you can massage all of these things into these blocks. So I will not spend time on it. Yes.
I like lost focus in the middle of this explanation of the S and B. But this SBN thing, it's like the F function, right?
The SBN thing, the execution of the program is the F function.
Right, yeah.
Not a single SBN thing. Or, yes.
Or like, in other words, we had like 2-bit addition, right? Which was like a function we wanted to
Yeah.
implement or whatever.
Yeah.
So now we care about implementing SBN.
No, not SBN. We are caring about implementing a program. So this is a program. And for the program, we are going to create an F function that represents the program.
Yeah. And what does the program take as input?
The program is going to take as input, like some part of the memory has the input and like some part of the memory has the output, and like that's it.
Okay.
So this is not like one norm, like the program is not in the memory. There is a separate program which is made of instructions of this form somewhere. It's not anywhere, but
Yeah, it could be part of the memory, but like we
we
don't
are going
need
to
that.
encode that program into the F function,
Yeah.
which will then operate on memory,
Yeah.
which contains the
Yeah.
input and intermediate.
But you could make the next step and say that like this is universal because you can treat the program as part of the memory and then like you're done.
Right. But then if you have a very long program that doesn't need much memory, then that is wasteful of memory. Like you don't, if
Yeah.
you wouldn't want to store the program.
Actually, it's like the whole blocking and everything is kind of done in a weird way, and it's not very detailed in how it's explained in the paper. So you have key value pairs, like your memory is represented in terms of like what's the address that you're writing the value to. So it doesn't have to be contiguous memory. That's not how you represent it. And yeah, this is a choice, yes.
Maybe it's not totally related, but I think, for example, these representation of F, these stuff, or people should have done this in not information theory, maybe coding, back in old days, for example.
I don't know.
But
The-
is that
the
in-
new part is just the training part. I don't think that there is anything other than that.
Mhm.
Like, I don't think that they have done that. That you run gradient descent to train a neural network to do a specific computation that you want to do. I don't think that anyone has done that.
Uh-huh.
Yeah, we knew how to set the weights of neural networks to do any specific type of computation.
Hmm.
But that was setting the weight, and that was not using gradient descent, everyone's favorite procedure.
About the setting, do we know how to set the weights, or do we know that it was, like there existed a set of weights?
Which setting?
Like we could actually set the
Here,
weights? No,
we-
before, like, what I mean.
Before.
Like, what I
No,
mean-
yeah, we knew how to set the weights. Like constructively, you can set the weights.
But I
A
guess-
lot of these proofs are constructive. They're completely constructive.
I guess.
It's not an existential proof. Like the existential proofs are even easier, but
I guess I'm just wondering what the point of learning anything that we know how to set exactly in neural network. Like then they just tell
because
us, oh, we could learn.
the point would be that, okay, gradient descent can be used for many things, and like learn natural language together with implementing functions. This is not going that far, but you know, like you're pushing the limits by not being comfortable by just saying that, well, I know how to set the weights, but can I? Like, it's gonna be, actually it's tough work to figure out how you can keep the number of training examples polynomial and the number of steps polynomial, and the result is not going to be completely satisfactory. If I get to telling you what the result is, I'm not happy with it. So they're not we can't even do this in a good way. I'm sure that we could do it better than done in this paper, but yeah.
I was just going to ask if when we set the weights, are those constructive methods efficient, like polynomial?
Yeah, absolutely,
So,
absolutely. Yeah. So it's completely superfluous to try to use gradient descent. It's more like an exercise to see that by using gradient descent, you're not losing anything. or not losing much. You're losing something, maybe a little bit, but not too much. I think that there was another paper that was claiming universality of gradient descent. I'm blanking on those. I think Emmanuel Abbé is one of the authors, and yeah, like this guy's in Apple, and in a way that was similar to this. I don't know whether these guys are citing it. Probably is. Hopefully. But that was even more artificial. Like I felt it was even more artificial than this one. It is also quite artificial. Yeah.
Do you, in the representation thing, when we set the weights, do we set it using examples? Like
No, not at all. Like we just know what computation we want, and like we just like figure out how to break it down into elementary parts that can be computed with a neural network, and like this part is doing that. And many times these neural networks are not even fully connected neural networks, but they're gonna be like weird. Like here you have this part and that part, you put them together, you kind of build up things. Well, of course you could say that like I can probably make it fully connected by introducing enough zero weights, and like sometimes people do that, but that's ignored. Yeah.
I'm still confused with this SBN thing. So this is saying that if we translate our algorithm into this SBN machine, then we can generate these data ABCs. And
Yeah, that's a translation. So translation involves generating the A's, B's, and C's.
And then this block loop machine can learn these ABCs.
So we're gonna take the ABCs, and we're not learning the ABCs, but we're gonna create training data with this blocking idea and this template matching iterative computation that does the same computation as what I described here. So this is the program, and we create this big vector blocks, different parts of the vector representing, instruction pointer, what values are where in the memory, and like stuff like that. Some of them are representing the instructions themselves. We need to know those because, well, when you're executing this thing, you take the next instruction, you have to look up the values of A, B, and C. Based on those values, you're doing all of these other things. You have to be loading that into the neural network somehow. So you create training examples for all of this. Separate blocks are associated with this. So this F becomes kind of giant, but it's still polynomial sized, and the training data is polynomial sized in everything that we care about. And once you have done that, you just run gradient descent, and somehow you get what you want. Exactly. So it's like not approximately right. Okay. Good. So this part is clear, right? And I'm not going to explain how these blocks are. There are like, I don't know, 30 different types of blocks to implement this little thing. So it's complicated. But it's kind of mundane as well. Like once you start to think about it, you would do it. You could do it. All right. So what remains is the learning part. So why can we learn these things? And how do we learn these things? And the lesson is that, well, this block structure is nice, but we want something even nicer, kind of more orthogonality to happen. And the lesson there that you can introduce this additional orthogonality at modest price. So we're gonna blow up these vectors to be something even bigger. And the reason for that is because we want every single template to be matched to be a unit vector that's orthogonal to everything else, because that will make training trivial. or easy, or we can prove things about that. So how to do that? Well, if every block, you have these 3 blocks, they need to be blown up based on how many templates correspond to those blocks. So this had 2 bits, but we had 3 templates that were associated with this block. So like we blow up these 2 bits to 3 bits. This first guy is going to be the first unit vector in those 3 bits. All the other bits are 0. This is the second, that's the third. Because we don't care about like, this is just representing inputs. And then we're gonna go to this bigger space and back to the smaller space when we're iterating this f. We can do that, it's easy. So now we create the training data based on just this blowing up things and orthogonalization. That's the training data that we use. Okay. Yes.
So is it like, for example, the range of the tau is not anymore k, it's bigger than
it's
k?
not.
Okay.
It got bigger, right?
Okay.
So like the sum of the TIs
Mhm.
is the new dimension.
That can be huge. Maybe like 2 to the k.
No,
Why not?
because for every one of these blocks, we are going to require that the support is small. So we will prove.
Oh.
So when you do that,
Okay.
when you represent your f with this block thing, then you show that all the supports individually are small. Of course, when you combine all of them in the blocks, you have this exponential size thing. So that's kind of, to me, the beauty of this, that you eventually deal with this exponentially sized space by dealing with the individual blocks one by one.
So the size of each block, is it going to be the max of the original size of the block and the number of?
I think
support
you can downsize it if you have fewer templates.
Yeah, but so okay, so just the number of templates, it becomes a
Yeah.
new size of the block.
Yeah. Yeah. It's just the number of templates associated with the block. So for the ice block, TI is the size. Okay. And then instead of taking these specific vectors, you just take the corresponding unit vectors. The output vectors remain the same. So we have this vector valued regression problem now, where all the training data are unit vectors. They're all orthogonal to each other. So we're kind of like a pretty lucky situation. Okay. But we're going to need to show that the f function itself is implemented by the neural network by creating these training examples, which don't contain all the combinations of the unit vectors and whatnot. Like we're creating the block-wise data, and then we are going to rely on the structure of what the neural network learns to say that, well, it happens to actually implement this function f. This is the or.
Wait, do we pick the data ourselves?
Yeah.
Oh.
Like here, you see how the data is constructed. So from this, I will create the vector. So this part is going to have like 3 bits. So 1, 0, 0. Like, okay, this is blown up as well, all the zeros. So that's one input vector. The associated output vector is kept to be this. For the next one, it's going to be the last 3 bits, 0, 1, 0. All the others are 0. That's my unit vector for the input. And this is the
Yeah.
associated output, and so on
Yeah.
so forth.
I didn't realize you picked the data then.
We are picking the data. We are constructing the training data so that we can load the function f into our neural network
So it's basically
with gradient descent.
It's basically like having query access stuff in the exact learning thing, where you can choose the access that you actually get.
It's more like teaching. It's like the learner is not doing anything. It's not
Right.
querying.
Yeah.
We are more like, I'm the teacher, I want you to know this. So I'm creating this very well curated set of examples
Yeah.
by which, after saying this, you will know what I mean
Mm-hmm.
on this exponentially many inputs.
Mm-hmm.
So that's a nice, powerful part. Okay. All right. So we create this curated data set. And what is the neural network that we are training? Well, here's a cheat. We want to train a 2-layer neural network or one hidden layer neural network with value activations without bias units. So I guess I don't do this. You remember this? So the neural network is going to be taking this X vector, it's how many dimensions we have, P, and it's applying value to W1 times X, so that's the size of the hidden layer. So W1 is I don't know, hidden layer times D, and W2 is going to be how many outputs, I think that was K, we're gonna need to have. And that's like this homogeneous one hidden layer RAU network. So far so good. You initialize the weights at random from Gaussians, IID, with appropriate scaling. And here's a dirty thing. You let the size of the hidden layer blow up. So they literally don't even study the case when H is finite. But they say, let's take the limit when H goes to infinity. Let's call the anti-K limit. It's an appropriate scaling. How to even understand that? Yeah, NTK stands for Euro Township Cutoff. Have you heard about this? No. Okay. So this is one popular way of bastardizing neural networks, so that they are amenable to theoretical analysis. We have a lot of randomness here. Something goes to infinity. Somehow the central limit theorem is going to overtake everything. It washes out everything. And somehow you normalize things in such a way that the limits do exist. So that you're summing a lot of Gaussians, like you're summing a lot of random variables, it becomes a Gaussian. That's the kind of thing that you're gonna have. And here, if H goes to infinity, then yes, you have a lot of randomness that you have injected into this thing. So effectively what this does is that the resulting neural network, in a well-defined sense, when you're training it with gradient descent, it behaves as training a predictor that works in a certain reproducing Kellner-Gilbert space. It works, it becomes this linear thing. So this is a linearization technique. So this kernel is, you have heard about these kernel machines and reproducing Kellner-Gilbert spaces and whatnot. They're these infinite dimensional spaces. You represent similarities of vectors within a product in these Hilbert spaces, And then you can do all the linear stuff. You're working with enough products and everything's well defined. And the limit of this process creates an underlying kernel, which you can write in an explicit form. I won't bore you with the details of how that kernel looks like. So with this, you are effectively working with linear machinery. So you're gonna take the squared loss, because the squared loss is a big friend of linear techniques. So you take your training data with the squared loss, you take this anti-K limit, and then there are some papers that show that if you use, so this is a Jason Lee and co-workers result from 2019, that shows that if you take gradient descent or SGD, small enough step size, or gradient flow, that's kind of the same thing. And you set the weight to minimize the squared loss on your training set, then the limit becomes the following. So in the limit, you get this random map. So this is a map from RD to RK. I use capital letter because it's random. Why is it random? Because it's based on this random initialization. Somehow the effect of the random initialization is not gone. You have so much randomness that it's not gone. And the properties of this is going to be that it gives you Gaussians. So if you take this random map and you look at the distribution of it, so the distribution of G, like, okay, so because J is random, you apply it to some vector input X, it gives you something random, it has a distribution. It's a distribution in K dimensions, and this happens to be a Gaussian. So this is a Gaussian distribution with some mean and covariance. So this is what they prove. It's a Gaussian with some mean and covariance, and they actually give a closed form for what the mean is and the covariance is in terms of the training data. So fully determined in closed form by training data. And the mean is going to look like linear regression, exactly like what you would get from linear regression. So take the Gramian matrix inverse, apply, blah, blah, blah. That's it. Covariance also something sensible that you would expect to see. So nothing really surprising there. After all, like, you're working in an RK just effectively. Okay, so we have this result, and so they want to use this result to get what they want. So they take the anti-K limit, and they want to argue that the mean can be used to decode what you want. So it's like if you apply a rounding procedure to the mean, then you will get exactly the bits you want. Okay. But this is random. So we actually do have a problem because we were applying this anti-K thing. This is random now. So we'll need to train not one neural network, but we have to train an ensemble of neural networks to reduce the amount of randomness that we have. So you can show that the mean is going to be kind of correct. It has the right sign. So based on the sign, like after some encoding, it has the right sign. So if you would just take the sign of the mean, then you would be good. But the neural network is not going to give you the mean. If you evaluate it, it gives you a random sample from this distribution. After all that training, you just get one random sample from the distribution. If you evaluate the neural network at the same input, you get the same random sample. Unfortunately, the randomness is due to the initialization. It's not due to like some inference randomness coming in. So you can't reduce the randomness that way. You have to train multiple neural networks. Now you're gonna take multiple neural networks, and what do? Like you average them, average the output of them. So if the variance was not too big, then you're squashing the variance. Once the variance is below how much the mean is separated from 0, you're kind of done. So that gives you the procedure. So now you have to calculate how many neural networks you will need to take, so that with high probability, the rounding procedure never errs. And so this is the aspect of the result that is kind of like squeaking a little bit, right? Like it's not a very clean result because now we're gonna need to worry about like how long this algorithm runs. If it runs ad infinitum, like every time you're calling this function f, implemented this neural network, you have to, the ensemble size would need to scale with that. Okay, it only needs to scale logarithmically with the number of steps the algorithm runs because you have union bounds and all that beauty, but still it needs to scale with that. And you only get a high probability result that says that with high probability, the calculation is going to be correct. So it's like, yeah, it was pretty promising until it flopped at the very end when we started to use NTK results, which are not quite doing what we wanted to do because we don't really have much better tools to show that with gradient descent you can actually force neural networks to implement what you want. But I suspect that maybe if you work harder with this orthogonal representation, with the RAU neural networks, maybe you don't have to take the NTK limit. It should still work. They run experiments. It seems to work.
So when you talk about like we have to worry about how long the calculation is, that's the calculation that's outputting the neural network, right? Not the calculation.
No, I'm talking about how long this program runs.
But why does that matter? Because at the end of the day, the randomness only comes from the initialization.
Yeah, that's the problem, right? And here you have this iteration of calling your neural network a large number of times potentially.
But there is some quantization.
If it starts to, what?
There is no quantization happening after each step.
So you could take a union bound over all possible inputs, or you could take a union bound over, yeah, why don't we do that? I guess.
Like, can't you just verify that like the machine has the right behavior and then you know it does and then it will just work for any calculation of any length? Because you know like the support functions, you know like it's a small number of functions, right?
I mean, yes, maybe a union bound over the input space totally works.
Yeah, because the input space is maybe proportional to the size of the program,
Yeah.
right? Or something.
Yeah, so you don't, yeah, I don't know why they're doing this, but yes, you're, I
But
think that
is
union bound
there
over the
some sort
input-
of quantization? Because the ReLU is not going to produce 0 ones, right? So there
Yeah,
is-
you are rounding.
Okay, so the rounding is happening after every step in the after
Yeah.
every step of that.
But like only the initialization induced randomness, so it's like,
Yeah, so the only
once your ensemble size is big enough and then your union bonds start to work, then, okay, no. Okay, so you're still like, oh, there is a good event and a bad event. The bad event is when on any of the inputs that you care about, the neural network is not doing what you want, right? And so if the probability of bad event happening is small, then you should be fine. So yeah, that's what you need to prove. And
And you
then
can
you're
just
done.
keep generating neural networks until you find, because you can verify that the neural network is correct easily. By
No.
just, because you know all of the support functions, you know all the tau i's, that you use to train a network. So can't you just run them through a network and
No.
just see if it's, why not?
No, the size of the domain is exponential.
But
Like
the number
that-
of
just
testing-
because the components are correct, the neural network is not learning the tau wise. The neural network is learning the whole F.
Okay, so it is not sticking to the
If you
block.
could somehow extract the tau wise from the neural network, then, but that we don't know.
What if
Like
you
you
just
can do.
break, so like you know that there are, okay, but the tau, so you can't impose any structural network to make the tau ice
Yeah.
ignore the rest of the block.
Yeah, so the problem would go away if we try to learn the tau wise independently, or, yeah, like individually.
Right.
Because you could verify each of them. And then it would be trivial. But here you just want to use one monolithic neural network that does everything for you. And this is the same story as before, like if you allow yourself more structure, then everything becomes a little bit easier and more manageable. But this additional structure is of course taking away generality and the possibility of generalizing outside of this specific domain, right? Like even this is not satisfactory at all because it only applies to this very specific encoding and like.
And I guess the remaining problem is that since this is a finite state machine, so it's got 2 to the n states, and in general the computation could be 2 to the m long. So you have to make sure that that error is like exponentially small in the size of the memory to guarantee that you're getting good results at the end.
But that's polynomial, so it's fine. Like, yeah. Like the log of the 2 to the n is just n, so it's like. Right? So the ensemble size doesn't have to be exponential in the number of bits or whatever. So that's fine. Okay. Yeah.
Is this exact learning come from that orthogonality they make? It's actually statistical
Yeah,
from.
yeah. I mean, when you're arguing about that the mu has the right sign, you're using that.
Mhm.
And actually, there are some dirty details that I didn't talk about because there could be some interference with the outputs. If you write out like what the regression function looks like, then you will see that there is some interference. And then you want to show that the interference is not too harmful. And that is specific to the encoding that you're doing with the training samples. And so there is some additional work that needs to be done. They have done that.
Mhm.
Yeah, I was just hiding that detail because, well, we can't really discuss those details, but there is that part of the work. So you can see that, like, this is a lot of work. It's kind of neat, but it's only going so far.
And the number of samples we need here is the input to one neural net times the ensemble size.
The times ensemble size doesn't like you use the same training set. Like
Oh.
you're not creating new training sets or
But
like
then don't
you
you
create
get-
a training set once and then you train, I don't know, 10,000 neural networks. It's the same training set and then average across those to get an output. Because you injected too much randomness and the only way you can reliably reduce the randomness is by introducing an ensemble. You only wanted the mean, but you're getting this variance. You want to get rid of the variance. That's linear in the number of the number of ensemble elements. Okay. See you then.